Welcome to this third German trainers talk today on Meeting C++. I work for KDAP. My name is Marc Mutz. I work for KDAP. We do Qt, OpenGL, and C++ stuff, and I'm one of the C++ trainers. So let's go directly into the talk. So in this talk, I will first define what partially formed means, and we'll give examples from C and C++. Then we will talk about moved from objects, especially the indirect int from Geoffrey Romer's paper and standard remove if. And that will lead us to the notion of safe and unsafe functions in the shown parent sense. Then we will have a look at composability. And here we will in particular look at flat map. And the last chapter is about C++20, where we now have concepts, and one of the concepts seems to change the way we need to write code, and I will hopefully tell you why this is not so. And if we then have time, I have prepared some bonus slides, a case study where we implement a pen with minimal overhead, implicitly shared. We'll have a look at weaker move semantics models. They exist, and whether they can be used. And if we have time, about exception guarantees, the so-called weak exception guarantee: is it needed, is it not needed? And in that particular case, standard variant will be the poster child. Disclaimer: all of the following. All the talk is about value types. That means if you're familiar with the terms regular and semi-regular types. This is not for RAI or polymorphic types, because we don't usually move them. And if you move a RAI object, you definitely want that you have a specified moved from state, meaning the RAI object is disengaged from its resource. So yeah. This is the program, and we start with this book by Alex Stepanov and Paul McJones. Came out in 2009, and I thought I would get rich on this because I have a copy of a first edition, hard copy, back from when it was in Edison Wesley or Pearson. And the prices on Amazon were skyrocketing. It was already more than $125 for the book. But then the publisher gave back the rights to Alex Stepanov and Paul McJones because it did not want to print another edition. And so now it comes out of Semigroup Press, which is somewhere in Mountain View, I guess. So probably Google has its hand in it. I don't know. And you can even download a free PDF version from that website that is mentioned there. And in this book, this is a math book. So Alex Stepanov treats programming as a subset of mathematics. And so this book is full with lemmas, conjectures, probably not, propositions, and proofs. And so he defines certain things, axioms, and so on. And one of those definitions that stands out very early on in Elements of Programming is this, where he says an object is in a partially formed state if it can be assigned to or destroyed. For an object that is partially formed but not well formed, the effect of any procedure other than assignment, only on the left side, and destruction is not defined, undefined behavior. A default constructor takes no arguments and leaves the object in a partially formed state. And he shows here TA semicolon, that is what we know in C++ as default construction. Not necessarily value construction, but he does not make a difference between the two, as you can see, where he says an anonymous object of type T, that is value constructed. So what do we take away from this is the definition of a partially formed state. An object is in a partially formed state if it can be assigned to and destroyed. So let's have a look at some examples here. Int semicolon. I is partially formed because the only thing that we can do with it is we can assign something to it, then we can use it. Or we can not assign to it, and then we must not use it except that it can run out of scope, so we can destroy it. So the only valid operations here are assignment of a new value and destruction. Everything else is undefined because it's uninitialized. So this is definitely partially formed. Now let's take the same example, but initialize the I with a 0. The question is I still partially formed? So the definition was an object is in the partially formed state if it can be assigned to and destroyed. Clearly, this can be assigned to and destroyed. So every object is partially formed as long as it's assignable and destructible if I have not deleted those operations. This is the EOP lemma 1.3. A well-formed object is partially formed. And this is also the reason why some people try to build up a straw man here and say that partially formed does not tell you anything, because every well-formed object is partially formed. So if you say partially formed, it can be anything. It does not contain any value, any entropy as a concept. And so to not fall into this trap, in this talk, I capitalize partially formed if I mean the following: known to be partially formed, but not known to be well formed. Right? So this is different. It catches the cases where the object, we know that it's partially formed, so we know that we can assign to it and destroy it, but we don't know whether we can do more. And this is often the case. So we don't know whether it's well formed. So int I equals 0, I is partially formed, but not capital partially formed. Next example, standard string. We know standard string. We know what the default constructed standard string is. It's an empty string. So we know that S is partially formed, but not capital partially formed, because we know that it's well formed. But this is only the case because we know standard string, right? And because standard string is a container, and we expect containers to not have a partially formed default constructed state, but an empty state. That is a natural ground state for the container to be in, and that is what we expect from containers. So, but if I give you, what happened now? I lost focus. Great. Okay, here we are back. So we were at standard string. And because we know standard string, we know what a default constructed standard string is. This is partially formed, but not capital partially formed. If I give you now the same thing with a rect, and you don't know what rect is, all you can assume is that R is partially formed, right? It could be well formed if this rect was an actual Q rect, which initializes itself in the default constructor, then this would be well formed, but we don't know, because we don't know rect. It could be just a struct of int x, y, width, and height. So here R is partially formed capital, which brings us to the first guideline. Unless you know that the type in question provides more, all you can assume is that a default constructed object is partially formed. Okay. So nobody forbids anyone to provide more than this, but if you don't know the type, or if you're in generic programming, you must assume that it's not more than partially formed. Next guideline, partially formed is a program state and not a bit pattern. This might surprise you. It kind of surprised me, but let's have a look at an example again. So here we have a pointer p, and we initialize it with a newt int. That int is initialized to 0, so everything is peachy. And next line, we delete the p. And then the third line, p is what? So we assume that we can assign to it and that we can destroy the pointer, not the pointee, the pointer. So we can guesstimate that this is partially formed. And yeah, in fact, it's partially formed, capital P, because the standard says so. In basic STC/4, it says that anything that you do with this is basically implementation defined. It's also an implementation choice to null out the P on delete. So you actually don't know what the value is. You don't even know whether it still has the bit pattern. But even if it has the bit pattern after the delete, the same bit pattern will now be partially formed state. And before it was a well-formed object. Yeah. So it gets better. If you took a copy of the pointer, when you delete the object through one of the copies of the pointer, all the pointer variables zap immediately, like a quantum wave function collapses on the measurement, and all of them become partially formed. And this is a problem for certain concurrent algorithms and localess implementations. If you want to know more about that, where the problems lie and the suggested fixes, they're linked to the paper by Paul McKenney and others, P1726, which discusses this in detail. Another example that you may or may not know from C++98 is input iterators. So here we have an input iterator that we got from somewhere, maybe the constructor. We take a copy, and then we advance the original iterator. And if you know your STL, then you know that input iterators are a bit weird. They are pretty weak because they basically model a file position in a file. And as you advance any of these on the same file, all the others get automatically advanced. So here, JT is partially formed. You can see the reference here on the input iterator. Table of requirements. This example is also in EOP and section 6.2. And JT, but not IT, is now partially formed. Yep. This slide contains a bug. Yep. Start next is start C++.
Hey, Mark?
Yeah?
We're noticing that the slides are not advancing for you. You're on example 2, P14.
Okay.
Seems maybe you're...
I guess I need to re-enable the sharing because the thingy has crashed. So how do I...
Or do you want to be on that slide?
No, I don't want to be on that slide. It advances for me, but I think Firefox has...
Okay.
Screen share. It has lost the screen.
Okay.
There we go. That should be now page 25.
Yeah. But
okay, so you did not see everything, yeah.
Yeah.
I will go back. Where did you say we were?
P14. So slide for page 14. Slide 14.
Okay.
Yes.
Right, that's where it crashed. Sorry about that. So we know that standard string default constructed is an empty string. So we know that S is partially formed, but not capital partially formed, because standard string is a container. So, but if I give you some default constructed rect and you have no idea what rect is, then all you can assume here is that R is partially formed. You know that you can assign to it and you know that you can destroy it, let it go out of scope, but you don't know whether it's well formed. If this is a QRect, it's well formed because the QRect initializes its members to 0, I believe. But if you just wrote a struct rect x, y, z width, whatever, then it's just partially formed. So the guideline, unless you know that the type in question provides more, all you can assume is that a before constructed object is partially formed. And partially formed is a program state, not a bit pattern. You have heard that this example with the auto pointer, with the pointer. So we allocate a new int stored in the pointer. Next thing we do is we delete the int through the pointer, and then the pointer, but not the pointee, is partially formed, because the standard says that the pointer is zapped, as Paul McKenney calls it in his paper. That means that any access through the pointer, but even the pointer value, is forbidden. It's implementation defined, but in a portable code, you don't even know whether p was not set to 0 to null pointer by the delete call. And if you had a copy of the p before, the q would now be immediately zapped together with the delete p. And this causes problems for concurrent implementations of certain algorithms and data structures. See P1726 for more. Another example that is also from C++98 is of input iterator. If you advance an input iterator, all older copies of the iterator become invalid. You can only assign a new iterator to it, or you can destroy them. But you cannot dereference them, you cannot advance them, nothing. So here too, JT can only be assigned to and destroyed. So JT is in a partially formed state. And this follows from the standard tab input iterator, the input iterator requirements. Two interesting things here. The first is, if I write this code with assuming that I'm being handed an input iterator, then I cannot assume more, right? Even if I'm actually given a forward iterator or a random access iterator, I need to assume that copies of iterators since advanced are partially formed, because that's the only thing that the concept gives me. Also, in C++20, we now have that the input iterator concept does no longer refine copyable. So input iterators need only be movable. But the compiler does not check this, because implementations of constraint templates are not checked to only use operations that are available from the concept. And so if you wrote this, you would not get a compile error. At parse time of the template, you would get one an instantiation time if you actually pass an input iterator that's only movable. So this is a slide where we rejoin. So here we use standard next, which takes an iterator, advances it by 1, and returns the advanced iterator. And this slide, I said, contains a bug, because what we're dereferencing is not the advanced iterator, which would be JT, but the original one, IT. And so IT is partially formed, so we're not allowed to dereference it. And interestingly, here we see the first example of safe and unsafe functions. Actually, the newer function, standard next, here is an unsafe function, because it leaves a partially formed object around. So it takes its argument, even by value, but once it has finished, its argument, even though it was passed in by value, has magically become partially formed. So this is an unsafe function in the sense from shown parent. How to fix this is to use the old version, standard advance, because that one takes the iterator by reference. So the any partially formed state, if it exists, is encapsulated inside the function and does not leave the function. So this is a safe function. And I find it amazing how Alex Stepanov got this one right in the original STL. And in EOP, he didn't. He writes a successor function there, which is basically what we have next. or we now call next. But in the original STL, the standard advance function, standard next was not available, was actually a save function. I find this amazing. So guideline. If you feel uncomfortable around partially formed states, avoid them. So for the default constructed state, you can use immediately invoked lambda expressions. And for delete and new, you can use standard unique pointer. But don't work around the partially formed state in the type design. The default constructor need not establish a valid value, because that would violate don't pay for what you don't use, right? And when in Rome, do as the Romans do, rather when in C++, do as the ints do. An int doesn't do this, so your type also need not do this. So let's have a look at the ile expression. Here we initialize the int, we switch over some condition, and we return various values, and the compiler will naturally warn us if it finds a control path through the lambda that does not return a value, right? So we can be sure that the int I is initialized, and that the use of it is well formed, is well defined. So if you instead of this, we must always initialize everything, thought group, then you might write this. So you initialize the value, then you switch over it, and then you use it. Of course, in line 8, you are sure that the I is initialized because that's what you did in the very first line. But you rob the compiler of ways to warn you if you forgot to assign a value somewhere in the middle, right? You probably know that if I would not initialize the int I that most compilers figure out and warn if they find a code path through the switch where the I is not set. So this is, if this could be extended to user-defined types, that would be great. And I think Herb Sutter's W lifetime work is a work in that direction. So we might get that actually. For the other example, we can just say make unique. We can even spell it correctly. And we actually get an error if we try to copy this. So we cannot copy. We can reset it, and that will reliably set the P to null pointer, so well formed. So we have hidden the partially formed state of raw pointers in a class that we can use. So, summary, be precise. Partially formed means it's destructible and assignable, but what we often mean by it is partially formed not known to be well formed, or partially formed known not to be well formed. And you need to distinguish these cases to have a meaningful conversation with other people. Partially formed objects exist in the language as early as kerning enriching C and C++. We have seen default initialized values. We have seen invalid pointers and copies of an input iterator since advanced. We have seen the following guidelines. Unless you know that the type in question provides more, all you can assume is that a default constructed object is partially formed. And partially formed is a program state. It's not a bit pattern. And if you feel uncomfortable around partially formed state, avoid it, but not in type design, only in your use of types. Here are some references for when you get the slides as PDF. So let's talk about move semantics. Consider the C++98 class. Yeah, so we have written this class not thinking about move semantics. We have written this in the aughts when we only had copy. This is from Geoffrey Raumer's paper. So because we did not have a shared pointer, we use boost shared pointer, and the class author in documents here a class invariant that mi is never null. And indeed, in C++98, that cannot be broken because the constructor always constructs a default, a valid shared pointer either it manages or it fails, then we get an exception thrown from make shared, and the indirect int has never started its lifetime. The author used the rule of zero, and in the equality operator, as well as in the streaming operator, he just dereferences the MI because there's a class invariant that says it's never null, right? So this was the introductory example in Geoffrey Romer's paper. There's a link later in the slides. And Herb Sutter, in February, I believe, wrote a blog post called Move Simply, where he calls this class buggy. Yeah, because as you compile this in C++11 with a move-enabled boost shared pointer, you get move semantics for free added. And those moved from objects that you then get have a null pointer shared pointer there. And that violates the class invariant. Yeah. I'm telling you, this is not broken. And to understand why I come to this conclusion, we need to go back 18 years to Howard Hinnan's paper N1377, which is the paper which introduced move semantics into the language. And we now know move semantics as a language feature, but there were tries, apparently from the paper, it's obvious that there were tries to make it as a library-only implementation. And when he reports about this, there's this quote from this paper: a pure library implementation of move semantics did not automatically move from R values, which is a really nice feature of the current proposal. Because this allows completely safe move semantics to come into client code with absolutely no code changes for the client. Okay, so the idea of move semantics as a language feature as opposed to a library feature is that a class like this is okay, and that temporaries and assignments and so on of temporaries enjoy move semantics automatically, transparently, and, he says, safely. And this is clear in a way, because how else can you make an R value if not by producing a temporary and binding that to something? And the temporary goes away after the end of the full expression, so it's not observable. But here's the guideline. Treat moved from objects as partially formed. Because this is the only thing that we can follow from this original intent. The intent is to have transparent move semantics for types that are unchanged from C++98, and that is only possible if you treat moved from objects as partially formed. Or, in the rephrased like guideline 1, unless you know that the type in question provides more, all you can assume is that a move from object is partially formed. Right. So the remove function, STL algorithm, is a bit peculiar because as an STL algorithm, it cannot actually remove something, erase something from the container. It can only reshuffle stuff and arrange for the elements that are to be kept in the front and all the rest that can be destroyed in the end of the range. That's what standard remove does. And this is C++98 code, and in C++98 this was completely okay because there was no move. And standard remove was swapping elements around until it got the order that it wanted. And so swap, of course, just exchanges two elements. And so after swapping, both elements are still valid if they were valid before. But in C++98, C++11, standard remove now moves instead of swaps. So the range between the result of standard remove and the end iterator of the container consists now of moved from objects. They are partially formed if you follow my rationale. And so this looping over it and streaming is no longer safe, right? Because this was crash. But this was possible in C++98, but it was already frowned upon. Very old guideline from effective STL from 2001. Treat objects in the range from that return from standard remove to the end as partially formed. Use the erase remove idiom. Of course, Stratemeyer did not phrase the guideline like that. He said hands off. Those are random values. You cannot assume any order there. But now we know what he really meant is partially formed, but partially formed, the term was only coined in 2009, so he could not have used it. So what's the erase remove idiom? That's here. So we do not even touch, store the value of that standard remove returns. We immediately pass it to the container erase. So we do not get into the situation where we might want to, access elements from the range as returned from standard remove to the end. And this is okay in C++98 and 11. And this is idiomatic code. This is what you should have written from the beginning. In C++20, of course, we now have standard erase, which, just like standard advance, is a safe function, because it completely encapsulates the partially formed state. It uses erase remove internally, but because it's internal, we don't get to see the moved from elements anymore. So this is a safe version of standard remove. And I have a conjecture. These remove-like algorithms, that is remove, remove if, and unique, as STL algorithms, are the only cases where moved from objects appear in a C++ program without an explicit cast. And casts can come up in various disguises. You have, of course, the static cast to an R value reference, or you have these function casts like standard move and standard forward, which, as you remember, they are not actually moving or forwarding. They are just casting from L value to R value. So these are casts, actually. And standard move is an unsafe operation. Jean Parent has been known to say this, and I believe him. And the interesting thing here is standard move is a cast. We know that casts break the type system. Yeah, they lie to the compiler to say, I know better than you. You know that this is an L value, but I want you to treat this as an R value. And I take the consequences. So if we reinterpret casts, we know that there are only limited procedures, operations that we can do on the return value of a reinterpret cast. And of course, for a given type, that might be more operations than for another type, but this is the same for standard move. We are casting here, so we should not be surprised that the result is not as usable as the input was. There's hope, though, because also standard move is an unsafe operation, but there's a safe companion, and you might not have looked at it, but at this like this. But it's true. Standard exchange is a safe companion of standard move, because standard exchange also does a move out of the original value, just like, well, standard move is just a cast, but standard exchange actually moves. So you know that the value is out of the original variable after standard exchange has returned. And you get to choose the new value of the variable as the second argument of the standard exchange. So standard exchange is safe in the sense that it encapsulates the partially formed state. There are no moved from objects visible after the standard exchange has returned. And I get to choose the new value of the moved from object, right? Here in this case, we have chosen it to be default constructed. And often this is roughly the same performance, because the compiler can see through all these things and optimize everything. Next guideline. If you can't tolerate the thought of partially formed objects, prefer C++20 erase if over standard remove if, and standard C++14 standard exchange X with default constructed over standard move of X. Or now we can say if you can't tolerate the thoughts of partially formed objects, prefer safe over unsafe functions. Move semantics summary. Valid C++ 98 programs become invalid C++ 11 ones unless you treat moved from objects as partially formed. Only then you can gain this free lunch that Howard Hinton mentioned in N1377, where the language feature gives us moves, transparent moves without changes to the client code. Guidelines that we have seen: treat moved from objects as partially formed. Treat objects in the range from as returned from standard erase, standard remove to end as partially formed. Use the remove, erase remove idiom, or if you can, use standard erase. Standard remove, a standard move is an unsafe operation, and so are standard remove if, and standard unique. And if you have paid attention, you might have seen that we have now found a safe variant for every unsafe function except standard unique. So anyone who wants to propose standard erase unique, it's still missing. If you can't tolerate the thought of partially formed objects, prefer safe over unsafe functions. And some references. So, composability. Composability is important in C++, in software development in general, because this is how we write programs. We take small programs and compose them into larger programs. And one of the problems with locks, for example, is that they don't compose. So that's why lock-based programming is hard, because two components independently written, independently verified to be working, combined, may not work. Right? Different order of lock of taking locks. One takes the locks in ascending address order and the other one in descending address order, and you can get that lock. So composability is important, and if we have mental model which works with composability, we have a much nicer day as programmers. So let's have a look at composition. The first thing I want to mention is that partially formed states are closed under composition. That means if you have a struct or a pair or a tuple, and one of the elements is partially formed, then so is the struct. Yeah. So here we have this vector and index. It contains a vector and it contains an int index that is set to be in a comment to be an index into the vector. So one thing is clear. If I just default construct such a struct, then it's partially formed, not well formed, because an empty vector does not have an index, a valid index, into the struct, into the vector. So first of all, the int index is partially formed in itself because it's uninitialized. But even if we value initialize the struct and therefore set the index to 0, 0 is still not a valid index into the container because the container is empty. So it's still partially formed, not well formed. And you can see we're using the defaults. We're using the language defaults. We're not doing something weird here. This is just the natural state of an int. It's the natural state of the struct. That's just how it is. If we create a well-formed object here in line 8, it does not work to highlight, okay. And then we move away from it, then again vi3 is then partially formed, not well formed, because the vector is empty, the index is what it was before, in this case 0, because for ints moves are copies. And so we are in the same situation that we were in the default constructed state. Yeah. And this is also something with a partially formed state, because the moved from state is the same as the default constructed state. That's something that should always strive for. But in this consequence, you can only reach it when both are partially formed. So here's the lemma. I'll skip over this because we're short at time. If you look in the standard and somewhere else, you will find that you get this valid but unspecified. So the standard says, unless otherwise specified, moved from objects are placed in a valid but unspecified state. And up to C++17, this only held for standard types. But many people believe that this should hold for all user types too, even if it requires extra work to achieve this. Yeah. So first, we need to understand what valid but unspecified actually means. And valid but unspecified means that you can apply all wide contract operations on the type. Yeah. So wide contract operations are those which do not have a precondition. Like, for example, vector.size doesn't have a precondition. So you can call it on a move from object. Right? So lemma 2, valid but unspecified is not closed under composition. No? So partially formed is closed under composition. Valid but unspecified is not closed under composition. Proof by contradiction. Assume that the lambda is false, so that it is closed under composition, then flat map would not need a custom moves constructor. So what is flat map? Here is basically a skeleton implementation of flat map from PO 429. So a flat map is like a standard map, but instead of allocating each node and storing key and value there, it has two independent containers, which by default are vectors. And so it stores keys and values contiguously in memory, and therefore we expect that lookup will be faster than if the nodes are strewn all over the memory. So we said that size would be one of the elements, the function that we can call. So we have two containers here, keys and values. So which one to choose? PO29, PO429 says to use the keys. But these containers that we pass in there, if they only guarantee valid but unspecified, the unspecified is the problem. They don't guarantee empty. We might like that, but they don't. There are actually certain combinations of standard vector with allocators for which this does not hold. So if we pass as KC a container which, when moved from, is not empty, and as VC a container which, when moved from, is empty, then we come into the situation that size can no longer return a valid value. If it returns key size, it's too large. If it returns value size, it's correct, but then we can have the same argument where we swap the containers around, and then M values will be too large. It could use the minimum of the two, but nobody does that. So with the default move constructor, this breaks. This can no longer have a valid but unspecified state when moved from. You need to do actual extra work. Can you still hear me? In this case, you need to move the containers. This is what the default move constructor would also do. And then you need to do the extra work, which is clearing. And this is extra work and probably measurable. But now you can assume that the key size will actually be okay to return. Yeah, so you need to do extra work here. Composability summary. Using the language defaults, partially formed objects composed are partially formed, but valid but unspecified objects composed are not valid but unspecified. Yeah, and the reference to the flat map example. Let's have a look at how and whether C++20 changes anything here. So we know that for standard moved from objects, they are placed in a valid but unspecified state. And this held in C++17 only for standard types. In C++20, we seem to require this also for user types, because standard movable, the concept that tells us that we can move an object, requires standard move constructible, which in turn requires in prose that RV state, resulting state, that's the moved from object, is valid but unspecified. Yeah. This clause has many more problems. For example, it talks about equality when comparable isn't even required, and it will be fixed. So for now, concept move constructible /1.3 can be ignored. It will be fixed, and no implementation can depend on this. Don't be scared about this. This does not mean that you can no longer write the vector and index struct. That's nonsense. But if we analyze this a bit deeper and look at what standard movable also requires, then we find that we need to adjust a bit our understanding of partially formed state. And I call this the Howard Hinand extension, even though he probably does not like it. But he came up with this, as far as I can tell, as the first person in the standard committee. So attributes to him. Element of programming swap works in terms of copies like the C++98 version did. Standard movable requires standard swappable. But in C++11 plus, standard swap uses moves instead of copies. So now consider self-swap, where I swap a value with itself. This need not be so obvious like here. I can have two different reference variables and they can alias themselves each other. So this can come up. So let's have a look at what standard swap then does. So we have LHS and RHS, which both alias X, and we move out of LHS into temp. That is okay. We move into LHS from RHS. Moving into LHS is okay because we are allowed to move into a move from object, but LHS is the same as RHS in this case. So we're moving from a moved from object. And this is problematic because that is not one of the operations that is allowed by the EOP definition of partially formed state, right? It explicitly said in the book assignment only on the left side. And then here, of course, we move back to temp. That's also okay. So how to solve this? There are two solutions. The first one is to make moved from objects self-assigned safe. A lot of words, but if you read this out 2 times, I hope you will understand what I mean by this. And this is always the case when you, for example, use the move and swap idiom. Or provide a swap overload found using ADL that's self-swap safe. Yeah. So the standard does not say that you need to use standard swap, the generic standard swap. You can also overload it. If you don't like this self-assignment safeness of the move assignment operator, then you can provide a swap overload, which is self-swap safe. And none of these usually require extra work, so it does not cost you extra code, performance, time, whatever, to make these both work. So guideline, prefer to provide an ADL swap overload that is self-swappable. Alternatively, ensure the move assignment operator is self-swap safe even in the partially formed state. As a library writer, you may want to avoid depending on a working self-swap. I know that some STL libraries have fixed self-swaps to not call them. I think it should be safe. So you should always apply this Hinand extension. But as a library writer, you might want to be a bit more careful and not depend on this. Guidelines. Ignore concepts move constructible 1.3, which will be fixed. Prefer to provide an ADL swap overload that is self-swappable. Alternatively, ensure the move assignment operator is self-swap safe even in the partially formed state. And libraries, if you write one, may want to avoid depending on working self-swap. And here's a reference to the C++ standard. So this was 50 minutes. And I have bonus slides, but I know that I will not be able to go through all of them. So there's a talk. I gave this talk, a version of this talk last week in the Munich user C++ group, where I go through all these missing slides, and that took 1.5 hours. So I would prefer if we just stopped here, and if you're interested in this pen, walk through to the pen class in the weaker models or the weak exception guarantees, then I refer you back to that talk in the Munich user C++ group. Thanks.
Okay. Thanks, Marc, for the talk.